Right, I'm going to show you two examples of how we can use a critical region and identify a critical region for a hypothesis test, and then use that critical region to come to a conclusion about that test. The first example I'm going to show you is going to be to do with a one-tailed test. The second example I'm going to show you is going to be to do with a two-tailed test. So if I just read the question out for the first example to begin with, it says, Jessica complains that a dice she's using is biased so that she's less likely to get a 6. She decides to throw the dice 30 times and test at the 5% significance level the hypothesis that the dice is biased against a 6. So already in that question we've got quite a few key bits of information that we just need to pick out. From this we can see that our value of n would be 30 because there's going to be 30 trials. We can see that 5% is the significance level, and we're trying to prove that it is biased against a 6. And the first part of the question is that we're going to write down our null and alternative hypotheses. Before we write those down, we're just going to sort some notation out here, and I'm going to write down that we are going to use x to represent here the number of sixes that she rolls. So because we're using a binomial to a distribution to model this, our value of n is 30. Our value of p is going to be 1/6 because that's the probability of her getting a 6. We can then say that x represents the number of sixes thrown. Okay. Now our hypotheses for this, firstly our null and then our alternative hypothesis. Our null hypothesis, remember, is always going to be an equality, and here that is going to be the fact that the probability is equal to 1/6. Our alternative hypothesis is something that we're trying to prove, and we're trying to prove that it is biased against a 6. So we're actually trying to show that the probability of getting a 6 is going to be less than 1/6. So that is our alternative hypothesis. And I'm also going to put here that this is the case where P represents the probability of throwing a 6. Just to be really clear. So there are two hypotheses there. For the second part of this question, we're then going to look at finding where or what the critical region is. So really we're looking at being able to identify the critical value, because we know that is on the limit of the critical region and the acceptance region, and then we need to use that and use our knowledge of that to then identify where that critical region is going to lie. The first thing we need to do is think about the value or our critical value and how we're going to be able to get that. And one of the key things to pay attention to is that our significance level is 5%. So we're looking at the value that for finding a probability less than this, the probability of that is going to be less than a 0.05. So let me just explain this. This is our p-value, and our critical value is the first value that we would reject for. Now, we're obviously going to reject for this test if the probability is less than our significance level, so less than 0.05. But our critical value is the first value that we reject for. So we want to find out what A is going to be here when we find the probability that X is less than or equal to A. It's smaller than 0.05. But we want to find the highest value of A. And that will be our critical value. So at this point here, really, we don't know what A is, and there's no other way to do this other than using some trial and error. So if we go into distribution on the calculator, and if we go into binomial CD, we're going to try and work out some different probabilities. For this, I'm going to use the list function, and I'm going to try out some different X values here for A to see which is the largest one that is below 0.05. Now, if we look at this value of n and value of p, if we times the two of those together, we would get 5. So our expected number of sixes would be 5. Our critical value is going to be less than that, we know that, so there's no point going above that because we're trying to prove that it is biased against a 6. So I would say let's only look at x values that are less than that. So in this list, I'm going to put in 5, 4, 3, 2, and 1. Let's work out the probabilities for all of those. And here we've got an n value of 30, and we've got a probability of 1/6. If we do that, that will give us the probability for all of these, for it being less than or equal to. And we're looking for the first probability that is going to be less than 0.05. Now, if we go down the list, the first one here that goes below is actually for our value of less than or equal to 1. That goes down to 0.0294. I'm going to write down the probabilities either side of this, and this is a really good thing to get used to doing. So I'm going to write the one above 0.05 and then the one below. So the probability that x is less than or equal to 2 is actually going to be equal to 0.1027. So that one's above 0.05, so we're not interested in that one. That will be part of the acceptance region. But the next one, the probability that x is less than or equal to 1 is equal to 0.0294, which is less than 0.05. So we can see that here a equals 1 is our critical value, and because a equals 1 is our critical value, that's the first value that we choose to reject for. Anything less than or equal to that is going to be our critical region. So our critical region here is for any values of x that are less than or equal to 1. Okay. Now in this particular example here, we were never given a test statistic, so we couldn't come to a conclusion for this test. All we could do was work out the critical region, but we can obviously see for any value of x less than or equal to 1, we would reject, and there would be enough evidence to prove that this dice is biased for this particular significance level. In the second example I'm going to show you, we are going to go on to look at a two-tailed test and how we can use that. It's going to be a little bit different to the other one because we're looking in two different directions here, but the principle and the process will be fairly similar. So if I just read the question out to begin with, it says, people entering an exhibition have to decide whether they turn right or left. The people organising the exhibition want to know whether there will be a preference for one of the directions. A trial run of 20 people found that 15 went to the left. Conduct a test using critical regions at a 5% significance level. So here we're actually being asked to conduct the test. So we want to come to a conclusion, and we're going to use critical regions to be able to do this. First thing that we're going to do is start with just sorting a bit of notation out. So we're going to use x here to represent the number of people who turn a certain way. And we need to choose here what we want x to be, whether it's either turn left or turn right. Now, because our test statistic is information on turning left, we're going to use or write x representing turning left. So x can be distributed binomially. A value of n is going to be 20. Our probability is going to be 0.5 because our assumption is going to be that the probability of them turning either way is going to be exactly the same. And we're now going to look and test to see whether there is a preference for a particular direction. And this is going to be where x represents the number of people who turn left. Okay, now we're going to write out our hypotheses using this. So we've already said our first hypothesis, our null hypothesis, is going to be that the probability is equal to 0.5, where P stands for the probability of turning left. We're going to assume that, and we're going to test to see whether they have a preference. So really, it doesn't say whether we're looking at turning left is more likely or less likely. So for this reason, we're just going to test to see whether our probability is not equal to 0.5. So this is where our two-tailed test comes in, because there we're using not equal to instead of less than or greater than. The only other thing we're going to note just before we move any further with this is that because this is a two-tailed test, remember that we need to halve our significance level. That significance level is shared over both the lower and the upper tail. So just note that our 5% is going to be divided by 2, and we're going to have 0.5% at each tail of this test. Now, in a similar way to how we found out a critical value in the last example, we're going to look at setting up an inequality and then being able to solve that to find out a value here to give us our critical value. But obviously, because this is a two-tailed test, we are going to be looking at finding two critical values. There is going to be a lower and there is going to be an upper. And we need to think about the two inequalities that we're going to need set up here to be able to find out those values. So the first one is when we're looking at finding the probability that x is less than or equal to a value of a is less than 0.025. 0.025 because that is our significance level at the lower tail. So in this particular question here, we're going to be looking at finding the highest value of a in this case. So we're going to be looking at finding the highest value of a, because that is going to be the first lower value that they're going to reject for. Now, looking at this the other way round, we're going to be wanting to find out the first value that we reject for at the upper tail. So that's going to be when the probability that x is greater than or equal to some value is less than 0.025. But now we want the smallest value of b. And that will be our critical value because it's going to be the first value that we would reject for at the upper tail. Now, let's look at this one to begin with, and this will take a similar process to the one that we did in the example before. So in our calculator, we're going to try out now some different values in our list, and we're going to have a bit of a look to see which of these we would firstly reject for. So if we just look at this test, we can see that our value of n is 20 and our probability is 0.5. So we are expecting 10 people to turn left. Because we're looking at our lower tail, we're going to be looking at values that are less than that. So I know that it's not going to be really close to 10. I know it's going to be a little bit further than that. So I'm going to start at 8, 7, 6, 5 and 4. And if it doesn't come in that, I can try out some different values, but I'm hoping that my critical value will lie within one of those. N is going to be 20 and P is going to be 0.5. And then don't forget, I'm looking for the first probability that is going to go below 0.025. So if I just scroll down here, I can see that actually it's this one. It's for our value of 5, the probability first drops below. So the same way as last time, I'm going to write out the two probabilities, one either side. So the probability that x is less than or equal to 6 is equal to 0.0576. And the probability that x is less than or equal to 5 is equal to 0.0206. So this value here is the first one that we would reject for. Therefore, a is equal to 5. That is our highest value of a. So that is one of our critical values. Now, we need to find out our upper critical value, our other critical value, by solving this inequality here, being able to find out what our smallest value of b would be that satisfies this. Now, this is a little bit different. Here it's fine because we're looking at x being less than or equal to a certain value. Our calculator can do that. But as we know, on the calculator, we cannot find the probability of it being greater than or equal to something. So I'm going to change this here so that it involves less than or equal to rather than greater than or equal to. Now remember how we would do this when finding a normal probability. Instead of finding out the probability it's greater than or equal to, we would do one take away the probability of it being less than or equal to the value below that. So the probability that x is greater than or equal to b is exactly the same as one take away the probability that x is less than or equal to b take away 1. They're both exactly the same. I'm now going to rewrite this. I'm going to rearrange it so I'm going to get this probability as the subject. So I'm going to add this to both sides and I'm going to take away 0.025 from both sides. And doing that will give the probability of x is less than or equal to b take away 1 is greater than 0.975. So I'm looking at the smallest possible value of b here that satisfies this. So I'm now looking at when this is going to be going above 0.975, and I want to work out what the value of b take away 1 is first. Then I can think about what b is going to be. And I want the smallest value that is going to be greater than this. So we're going to have to change our values here. Because we're now looking at the upper tail, it's going to be a much higher value. So as where before we were looking around 8, 7, 6, 5, we're going to be looking at above 10 here. And thinking about the other values that we've got there. And again, I'm just going to pick some at random, and if we need to rethink or look and change it, then we can do. I'm going to use 16, 15, 14, 13, and 12. And I'm going to work out the probabilities that x is less than or equal to those. If the first one that goes above 0.975 is not there, then I can change those values. N is 20 and P is 0.5 are still exactly the same. So the first one that goes above 0.975 is going to be 14. We can see that's 0.9793. So I'm going to write out the one below it and the one above it, like I did in my other example. So the probability that x is less than or equal to 14 is equal to 0.9793. And the probability that x is less than or equal to 13 is equal to 0.9423. So 14 here is the first value that is above 0.975. So that tells us that b take away 1 is therefore equal to 14. Now if b take away 1 is equal to 14, obviously b is therefore equal to 15. Okay, so this tells us that 15 is going to be our other critical value. So we found a lower critical value of 5 and a higher critical value of 15. And we can use these two to now write out our critical region. So our critical region will be more extreme than these two values, and it will include these two values. Remember, the critical values are included in the critical region. So one inequality to represent the lower part of our critical region will be the fact that x is less than or equal to 5. And for the upper part of the critical region, any values of x that are greater than or equal to 15. So we've got our critical region stated there. The last thing that we need to do is come to a conclusion, because remember that we were given a test statistic within this test, and we can look and see whether there is enough evidence to prove that there was a preference on turning in a certain direction. Our test statistic here was 15. If we look back at the question here, we had 15 people that turned left. Is 15 in our critical region? Yes, it is, because the critical region is if x is greater than or equal to 15. So we will write that x equals 15 is in the critical region. So we are going to reject our null hypothesis. And if we're rejecting our null hypothesis, then we are saying that there is sufficient evidence to suggest there is a preference for one direction. Now, interestingly, we can see that it was 15 people that turned left. So we can see that there is a preference towards turning left, but we don't say that in our conclusion. We were only testing to see whether there was a preference of turning one direction more than the other. We're not interested on whether that's left or right. All we're interested is that the probability of turning one way is higher than the other. And because this was in the critical region, we've proved that there is sufficient evidence to show that.